Welcome back to the course Imperative Programming I2204, and let us begin a new chapter, Chapter 2, Pointers and Arrays. We will begin by pointer definition. What are pointers? A pointer is a variable, as simple as that. A pointer is a variable that holds a memory address. So this is a pointer here on the schema. It is a variable called p and it can hold a memory address. Let's suppose this memory address is 1001. This address is the location of another object in this memory. This typically another variable in the memory. Let's suppose this address is the address of the variable x, which is also in the memory. And this is the memory. Okay, so p and x are both variables in the memory. X has the value 3, is a variable that has the value 3. However, P has a special value, which is the address of X in the memory. So this is it. You know now what is a pointer. If one variable contains the address of another variable in the memory, we say that the first variable points to the second. In my schema here, the variable P points to the variable X because P holds in her value the address where X is located inside the memory. So in order to make things appear schematically, we will draw an arrow that goes from where the value of P was supposed to be into the beginning of the variable X. So into the upper left corner of the representation of the variable X in the memory. I don't want to know what is exactly the address of X, so I will erase this information from my schema. So now P is a pointer and it holds the variable X's address, and other variables and other memory spaces that are unused until now in the memory, I will also erase them. So this is my schema now. I have two variables. One is X, the other is P. The variable P is a particular variable. It holds addresses, and this time it is holding the address of X inside the memory. So this arrow base is not a syntax in C, but this is used here schematically in order for you to remember that P is pointing to C. Pointer variables. How do I declare a pointer? A pointer declaration consists of a base type, an asterisk, and the variable name. Type, asterisk, name. Example, int star p, and of course the declaration ends with a semicolon, or char star q. Here p and q are both pointers. You will wonder why is the base type used for, since p and q are both variables and the memory needed to store memory addresses in p and q are the same. So what do we use the base type for? So technically any type of pointer can point anywhere in the memory. However, the pointer arithmetic is done relative to its base type. So whenever you want to do something with the pointer, you need to know what is the base type of this pointer. We will see now. So it is important to declare the pointer correctly. Go to section 2 and see the pointer operations. The two special pointer operators are the addressing and referencing operator, which is the ampersand symbol, and the other operator is the dereference operator, which is the asterisk symbol. Addressing or referencing operator, the ampersand operator, operates as following. Given a variable C of type T, let's suppose on the schema it is an integer, the ampersand operator is a unary operator. It needs one operand only that returns the memory address of its operand. So we put the ampersand in front of any variable C, and the value of this expression is the address of this operand in the memory. So if I say the affectation M receives the address of C, this means M is a pointer and M point to the variable C in the memory. We can state that M receives the address of C. We can also read this expression as following. M references C. We can also say that M points to C, and M is a pointer and C is its pointee. So all these expressions are equivalent and they read the following expression, which is m equal and c. So we can deduce that if c is of type t, m, in order to be able to point to c, it must be of base type t. Dereference operator asterisk is applied to a pointer m of base type t. The unary operator asterisk gives the value of the object of type t pointed by m. So here, if m is a pointer and the object pointed by m is c, the unary operator asterisk, when applied to m, will give us the value of c. Asterisk is the complement of ampersand. If you write q equal dereference m, we read q equal asterisk m, we will operate as follow in order to execute. We have a variable q in which we will copy the value of the pointee of m. We read dereference m and place its value in q. We can also say retrieve m's pointee value, which is 3, and put it in q. Let's pass now to examples, and let's consider this one, which purpose is to demonstrate the importance of the base type for pointers. So here in this example, we have a main function declaring 3 variables, x, y, and p. Let us see it in the environment. This is a variable x equals double x equals 100.1 and double y, and another declaration of another variable, which is the pointer p. We declare it like that: double space star p, or double star space p, or double space star space p. So all these syntaxes are correct, except for the syntax when you put a double star p without spaces at all. So this is our pointer declared, and this is our variables x and y, and then I am referencing x and putting the value in p. As I told you, we read p points to x. And then I am dereferencing p and putting its value into y. So we read y receives the value of the pointee of p. So how do we do? I draw the memory space for you. This is x, and this is y, and this is p. We have initialized x to the value double. This is a double variable. We initialized it to the value 100.1, and now we will make p point to x. So p is a pointer, it points the variable x, and now we say p is a pointer, x is its pointee, p points x, etc., etc. And then we said y receives the content of p, or the value of the pointee of p. So we will copy paste the value of x into y. So whenever I want to print the value of y now, I know it is equal to 100.1. Okay, so whenever I will run this program, I will have the same thing. This is not surprising. This is demonstrating that everything is normal. If we continue with this example, we will alter it a little bit to change the base type of p into int, and this is the purpose of the example. Continue with the altered example this time. This time we have to change the base case of p into int instead of being the same base case of the variables x and y. So let's write int star p, and before we wrote int star p, everything was okay. We had the value 100.1, and since I write int star p, the compiler began to complain: incompatible pointer types assigning to int star from double star, etc., etc. Why is he complaining? Because he knows that When I want to run this, ignoring the warning, I will not get what is expected to get. I will get another value other than the value of x. Although here I didn't change anything except for the base type of p, I'm still copying the content of p. What is really happening inside the memory state? This is the case where you need to draw the memory state in order to understand what has happened really. So we go to the memory state and I will show you what happened. When we said that p points to x with the base type int and then we copied into y what points p2, we copied only the integer part of x because x is a double, it has double the size of an integer. When we said that p is of base type int, and then we dereferenced p to copy the value of the content of p, it means the value of the pointee of p, the compiler understands that the pointee of p is like the type of p, so he copied only the integer part of this number, and this is the number 100.1 in binary. Okay, this is the number in binary. If you convert 100.1 decimal to binary conversion, you will get this one. So he will copy only the first one into y, which is double. So the y variable also has another part which remains uninitialized. So there is garbage value here. You don't know what there is here. The arbitrary values, the old values before the memory allocation. So that's why we got another number, another double number, whose beginning is the same of x. In binary, I am saying. So if this number is the following, I have already converted it using the converter. They have both the same beginning, the same left part of the double, but not the complete values. So this is what has happened, and this shall demonstrate that if you don't have the same base case as your pointee, you will get into troubles. Operation is the pointer assignment. Let's consider this empty program which we will be filling slowly. Here we are having 5 variables, 2 of which are normal variables and 3 pointers. And notice here when we declare 3 pointers, we have to put 3 times the asterisk. Every time I have a pointer, I have to precede it by the asterisk. Because if I write int star p1 comma p2, p2 will be considered as a normal integer. So here are my variables x and y, both initialized to 3. P1, P2, and P3 are pointers, but we don't know yet where they are pointing. Okay? Not just because we put asterisks that they are pointing somewhere. They still are uninitialized. And then I say P1 receives the address of X. So now P1 points to X, as you can see on the schema. And then here is the purpose of this section is when you do assignment between pointers, when you do the equal sign between P2 and P1. So how do we read? We read as usually P2, the variable P2 receives the value of P1, just like as if I said y equals s, the variable y receives the value of x. And now I am saying the variable P2 receives the value of P1. How do I draw this? The value that is in P1 is copied into P2. So P2 also points the same thing as P1. They have the same value inside them. So P2 points X now. I can now understand the schema, and before I continue it, I want you to know how to print the values of a pointer. So in order to be sure of what I'm explaining to you, You can now, I will recapitulate, we have 5 locals, 2 initialized ints and 3 pointers to ints, and here p1 points to x, and here the p2 equal p1, which we read p2 receives p1's value, and they both now share the same pointee and point to x. You can print the value of the pointee of both pointers, dereference p1 and dereference p2, and you can, to be more sure, because they maybe p2 point to y and the value of y also is 3, so you can print the value of the pointers themselves, and it is %p. So if you print %p p1, %p p2, this will print the value and not the content of p1 and p2. If you want to print the content, you print dereference p1 and dereference p2, which are of both of type int. You can also print the address of x, and you must have those 3 values to be equal, because p1 stores the address of x as its value, and also p2 because it copied it from p1. And you can print the value of x, of course. And lastly, we can say p3 reference to y. If we print the content of p3, it will be equal to 3, but if we print the value of p3, it will not be equal to p1 or p2 or the address of x. This is another variable in the memory that p3 holds its value. P3 and has the value of the address of y. So these 2 values will be equal to each other, but not to these 3 values. And here is our program. I already run it, and you can see the content of P1 is 3, the content of P2 is 3. The value of P1, we give values in hexadecimal values, so this is hexadecimal, and this is the same value, %p, P1, P2, and address of x. The value of x is 3. The content of P3 is also 3, and the value of the pointer P3 is another hexadecimal value other than the previous, which is the same also of the address of x. And in this simple program, you learned how to deal with pointers. They are ordinary values, ordinary variables. They can reference other variables. We can dereference them. We can reference the variables. We can assign one pointer value to the other. This is very easy. So let us continue our schema, and let us read here before we continue the schema. Use the %p format specifier inside printf to display an address in the format used by the host computer. And this is our final schema in which we made p3 point the y value. So let's code. We already have coded this example, and let's now move to pointer arithmetics. In pointer arithmetics operations, there are only 2 arithmetics, the addition and the subtraction. Example. Let P1 be an integer pointer with a current value of 2000. Let's suppose it is 2000, hexadecimal or not. Assume integers are 2 bytes long. Why do I say assume integers are 2 bytes long? Because in C language, the sizes of the primitive types are not fixed. They are left to be fixed by the operating system and the platform. So every machine can have a different size for the type int, for example. So assume the integers are 2 bytes long, and if we post increment p1, if we write p1 plus plus, knowing that p1 is an integer pointer, is an int star p1. So when we do this, p1 will not contain 2001, it will contain 2002. Why? Because we need 2 bytes to store an integer. So if P1 refers to the address 2000, the next integer after this address will be on the address 2002, because 2000 and 2001 are occupied by one integer. So each time P1 is incremented, it will point to the next integer. Here, the integer because base type of P1. The same is true when we decrement. So let us take an example and a visual example here, and let us consider that we have two pointers, char star ch, which is equal to 3000 in hexadecimal, let's say, and int star I, which is equal to also 3000. So basically, ch and I both point to the to this 3000 variable here in the memory, to this address in the memory. So this is ch. If I say ch plus 1, it will be the next variable in the memory. Why? Because the characters occupy 1 byte, suppose. If the characters occupy 1 byte, then we can store here 7 characters. However, for integers, we can store 1 at the address 3000, which will occupy 2 consecutive bytes, the other at the address 3002, and the next one on the address 3004. And next, you cannot hold one full integer, it's a half of an integer. So, what I am saying here is that the same memory, either it can hold 3 integers or 6 or 7 characters. So this is a pointer arithmetic. Whenever you increment or decrement a pointer, it decrements to the next place or to the previous place of the base type. You may add or subtract integers to or from pointers. For example, you can say P1 equal P1 plus 12. It means from where P1 points, skip 12 places to the next place. You may subtract one pointer from another. You may say P1 minus P2 in order to find the number of objects of their base type that separates the two. So if P1 points a certain memory place and P2 another memory place, you can subtract those pointers in order to know how much elements can be held in between those places. Of course, always referring to the base type. All other arithmetic operations are prohibited. You may not multiply or divide pointers. You may not add two pointers. You may not apply the bitwise operators to them. And you may not add or subtract type float or double to or from a pointer. You cannot skip 1.5 place of integers, for example. So let's take an exercise in order to understand what I am saying. This is the program. Int main, I have pointer of base type int star p equals 3000, star q, another pointer of base type int, two pointers of base type double, two pointers of base type char, one of each is initialized and the other is left uninitialized in order to do operations on pointers on them. Since in C language, the actual values of the size of different primitive types depend on the implementation, let's do this supposition. Suppose the following table is true. Suppose that the primitive type double occupies 8 bytes in the memory. The primitive type int occupies 4 and the primitive type char occupies 1 byte in the memory. And the question in this exercise is continue the memory state for each of the instructions. Note that in practice, you are not to assign static value to pointer variables. You are not to do this in practice. You cannot write p equals 300, r equal 500, 5000, etc. Because those are pointers to point variables in the memory, not to point static values. This code is only used to show you the memory behavior. So I wrote this code only to show you if, for example, P had the value 3000, what would be the value of Q if I write Q equal P plus 4. So here are our 6 variables, P, Q, R, S, T, U. They all have the same size, but they all differ in the base type. So P and Q are of base type int, R and S are of base type double, T and U are of base type char. If I say Q equal P plus 4, what is the value of Q here? Is it 3004? No, because this is what we are explaining. It is the value of P plus 4 places to hold int, and every int occupies 4 places. So it would be 3000 plus 4 times 4, which is 3016. Consider now S equal R minus 3. The same applies to S, where S is of base type double. So you must go back in the memory 3 places of double, where double occupies 8. So here is the value of S, 5000 minus 24. And next, U is T plus 2, so it is 2000 plus 2 times 1. As pointer comparison, you can compare also two pointers in a relational expression. You can write if P is less than Q, print F P points to lower memory than Q. Here P is less than Q, so it will print this message. Used when two or more pointers point to a common object such as an array. So you can put it like here in this simple example, but normally you compare two pointers when one point an element address and the other point the next or the one after some elements or the previous, and you want to know which element is before the other, so you compare the pointers. In previous exercise, the expression P less than Q returns true. S greater than or equal to R returns false because S is less than R. And T equal to U returns false. They all are valid and they do return some answer. So you can compare one pointer to the other. Exercise for the next time, you have to draw on the memory space, just like I did for you all the lecture, the following memory state for the following exercise, especially for the lines marked with 1, 2, 3, 4, 5 with the asterisks. And then you will give me the screen. So I already have put for you the Excel sheet on which I am solving. You can take this Excel sheet, download it, and use it to solve this exercise. This was about the first two sections. Next, in the next video, we will talk about the rest of the chapter 2 sections, and especially we will begin by the null pointer.